All right. Last lecture, we talked a bunch about game tree evaluation, and I used that to show you this interesting sort of relationship between deterministic, non-deterministic, and randomized algorithms. At its core, what was going on was that in this game tree, at any particular move in the game, right, there were two choices for a player, and one was good and one was bad, right? And the non-deterministic algorithm would always make the good choice. The deterministic algorithm would always make the bad choice. And the randomized algorithm would sort of have a 50-50 chance of starting with the good choice or the bad choice. Now, I want to fill this in a little bit. With each of these, there's something I want to say. First of all, talking about the deterministic algorithm, right? What do I mean when I'm saying that the deterministic algorithm is always making the bad choice? The way I described it was that you have this deterministic algorithm which is sort of probing, checking one subtree, checking the other subtree, so on and so forth. And I sort of was allowing the adversary to adaptively respond to the queries that the deterministic algorithm was making, right? If the algorithm starts by investigating the right subtree, then the adversary puts the answer in the left subtree and vice versa, right? Now, it seems like a very powerful adversary, right? That it can be sort of adapting all the time, right? Usually you think of an algorithm as just receiving an input, right? And then you run the algorithm on the input and you look at how it did, right? So how do we bridge from this notion of an adversary that is dynamically making choices to our sort of normal model of just having an input? And in particular, can we say, based on our argument about an adversary, that the worst case behavior of the deterministic algorithm, that there's some input that will cause that algorithm to take the 2 to the h time that we found, or sorry, the 2 to the h or 4 to the h over 2 times. How do we get from adversary to input? Does the question even make sense? If it doesn't, then ask. Yes? Yes, absolutely. So in general, when we talk about the runtime of an algorithm, we're asking about the worst case performance over all possible inputs. Yes? But when I talk to you about this deterministic algorithm and how we were going to make it slow, I introduced an adversary, right, that was actually making its choices about what to answer the algorithm while the algorithm was running. And so this doesn't really completely fit our standard notion of, is there a single input that causes the algorithm to run poorly, right? The input doesn't have an adversary coming along with it. It's just an input. So how do we bridge from the story I told about an adversary to argue that there is a bad input for the algorithm? Yes?
Well, I mean, once you do the input, having the adversary, you know what choice the adversary made, and you can just make the input to just already have those choices, I guess, baked in.
Exactly. So the bridge is that the story that we're telling about the adversary is that the adversary is providing answers is sort of filling in certain parts of the input as the algorithm runs. And when the algorithm is done running, the input will be completely filled in, actually, because we showed that the algorithm is going to have to look at all of the input values in the worst case, right? So the trace of the adversary's responses provides a single specific input on which the algorithm will do poorly. And of course, it's a deterministic algorithm. It runs the same all the time. So if we give it that input, its behavior will be the same as the behavior it had when it was dealing with the adversary. Does that make sense? Okay. So what we can say here is that the trace of the adversary's answers or choices gives us that worst case input. Yes? Okay. Now, with the sort of non-deterministic algorithm, the story is very straightforward, right? Here, we showed that no matter what the input is, the non-deterministic algorithm is always going to look in the proper tree first, and so on and so forth. With the randomized algorithm, where these random choices are being made, you can also ask about an adversary model for the randomized algorithm, right? And once you have randomization, there's actually an interesting question you have to answer, which is whether the adversary is aware of your random choices. Okay. And so there are different models of adversaries, and those of you who took advanced algorithms with me last year saw this before, right? We talked about oblivious adversaries, where they must specify the input without knowing my random choices. Okay, and since they are oblivious to the random choices, this makes the randomization very powerful. Okay, but in contrast, you can talk about an adaptive adversary, and there are actually two kinds. The unreasonable kind is what you call a fully adaptive adversary. And this one knows all the random choices I will ever make. So essentially, the fully adaptive adversary knows the random string, the random advice string that I am using to run my randomized algorithm. Okay? And in general, against a fully adaptive adversary, randomization is not particularly useful, because if the advice string is known, then essentially from the perspective of that adversary that knows the advice string, it's essentially a deterministic algorithm. Right? Once you fix the advice string, the thing that is providing the random choices to the algorithm, if you fix that, what you have is a deterministic algorithm. And we will return to that idea. There's an interesting middle ground of what's called a partially adaptive adversary, which knows your past random choices, but not the ones you're going to make in the future. So it knows sort of the state of the current state of the algorithm, right? All of the inner variables and things. And this is a model where randomness can still help you, right? If the adversary is trying to plan out a trap for you, right, your random choice still has a chance of taking you out of that trap, because until you're in it, there's an opportunity for you to wiggle out through randomness. It also kind of makes sense in practice, because a lot of times in modern computer systems, the choices of an algorithm influence the future, right? Because we have these very complicated systems which, for example, incorporate swapping and paging and time sharing and so forth. And so if an algorithm chooses to do one thing, it may run for longer before getting swapped out. If it chooses to do a different thing, it may run for a shorter time before getting swapped out. And so the choices the algorithm makes actually influence the future state of the system. And so it kind of makes sense to imagine the adversary having some sense of this, like, this is too much knowledge, right? In the real world, the adversary won't know everything about your algorithm, but it still is kind of a plausible story in practice. However, I'm going to generally focus on these oblivious algorithms, which just don't have any awareness of your random state and are trying to give you a worst case input without knowing what choices you're going to make. Yes? The oblivious adversary is required to, like, it knows everything about your algorithm and your plans and what your randomized algorithm is, but it doesn't know what your choices are going to be. And you then allow the adversary to construct as bad an input as it wants to, but that's before your algorithm makes any random choices or before it knows about any of the random choices your algorithm is making. That is what we have been looking at. That's right. I just wanted to formalize it. Any other questions? Yes?
If your choices are independent every time the algorithm runs, what's the difference between partially adaptive and oblivious?
If your choices are, well, the point is that if you're talking about multiple runs of the algorithm, then a partially adaptive adversary will know about what happened in your previous runs, but that doesn't matter in your story. But they will also know as your algorithm is running, sort of halfway through the current run of your algorithm, they will know what your current run did.
Okay. I thought it was just past trials.
No. So this is not related to amplification. This is really about a single run of an algorithm and what it is aware of as the algorithm is running. Yes.
So I'm just trying to understand a little more. So I guess can we kind of compare like partially aware algorithm to like kind of being like sort of online kind of like it's.
That's right.
Okay.
Yes, partially oblivious. It's kind of like the adversary is trying to be an online algorithm that is responding to the behavior of the algorithm. Okay. All right. So we left off with this with this demonstration that there were these different runtimes. I should put them up at the top. There were these different runtimes for these 3 different algorithms, right? The non-deterministic algorithm had a 2 to the h/2 runtime, and the randomized one, I think it was this. I should go look it up. It was something in the middle, which was about 0.75 instead of, it sort of gave an n to the 0.75 instead of a over 4. So this was about root n, this was about n to the 3/4, and this was n. Okay, so that's what we showed last time. But I left us with a question, right? For the deterministic algorithm, we proved a lower bound of n, right? In the usual way, we demonstrated that you have to look at everything. Showing that the non-deterministic algorithm is optimal is also not that hard to sort of demonstrate that you need to look in order to prove that there's no flexibility left in the outcome. But how do we show that this weird result for the randomized algorithms is tight, right? How do we show that there's no better randomized algorithm? Or equivalently, how can we give a lower bound on the runtime of a randomized algorithm? Yes? So when we're working with deterministic algorithms, we say, here's an input that the algorithm runs very slowly on, right? But with randomized algorithms, there's randomness. If I specify an input, I still have to analyze there's like this whole probabilistic phenomenon of what is the expected time for the algorithm on this input, which makes it harder. So I'm going to show you a really cute trick that Andy Yao developed. We're going to use this technique called Yao's minimax principle. For lower bounding randomized algorithms. And this is going to let us take another look at games. So we were just looking at game trees. Now we're going to look at a different facet of game theory. Okay. So I described this game last time as based on a tree with moves and wins and losses and so on and so forth. But now we're going to think about what's called the extensive form of a game. So the extensive form of a game asks each player has a choice of what are called strategies. A strategy is simply for every possible state where they move, their choice of move. Okay? So you're basically asking the player to write out their complete plans for how they will ever play this game. Okay? So in our game tree, what does a strategy look like for player one? What does player one have to specify so that they can leave and let somebody else play for them? Yes?
Like at every possible node, which way they're going.
Exactly. They have to say for each node where it's their turn, which move are they going to make? In other words, which child are they going to move to? Okay? So if I have such a strategy for each player, right? The game can be executed. Right? Whichever player goes first, their strategy book says what they do. Now the game is in a new state. The next player, the player to move now, you look in their strategy book and do what they say to do, and so on and so forth. So basically, if you just have the strategy for each of the players, you can play the whole game without the players there. Yes? Okay. Of course, there are many strategies. Right? And you would never do this in practice, but it's a very useful model for thinking about the theory behind games. Okay. So you have this whole collection of choices, right? And the simplest story to tell for game playing is that you have what are called pure strategies. Actually, these are what I described above. Right? A specific move for each position. And these pure strategies are deterministic. And that's fine for some games, right? The strategies in our game tree were deterministic strategies. But let's think about rock, paper, scissors. Okay? What are the pure strategies for the game rock, paper, scissors? Yes?
Choose rock, choose paper, choose scissors.
There are 3 strategies, right? Because this is a game with only one move. You choose rock, you choose paper, or you choose scissors. And I claim that none of those strategies is very good. How come? Yes? Exactly. If your opponent knows your strategy, they have a so-called best response. Often beats you. Right? So you pick a strategy of rock, you put that down in your strategy book, your opponent peeks at your strategy book, and you say, okay, and the opponent says, okay, I'm going to put paper in my strategy book. And now your opponent wins all the time. Even worse than that, you're going to look at the opponent's strategy book and you're going to say, wait a minute, no, my strategy book is scissors, not rock. Right? And then your opponent is going to say, no, wait a minute, my strategy book is rock, not, right? And so you get into this situation where there is what we will say no equilibrium. Okay. The strategies will keep changing in response to each other because there's always a better response on the other side. Now, Von Neumann was one of the smartest people in history. You should read about von Neumann. He's kind of incredible. The range of things that he figured out in different areas. I mean, he did really fundamental work in computer science, but also worked on the Manhattan Project and helped build the atomic bomb and everything in between. But he developed game theory as a field. He has the seminal text, von Neumann and Morgenstern. And what he observed is that you can talk about what are called mixed strategies. Okay. A mixed strategy is a probability distribution over pure ones. Okay. And he proved some really interesting results. He proved that if you have a two-player zero-sum game, and I'll fill in what these mean, always has equilibrium mixed strategies. Okay? So two-player is obvious. Zero-sum means player one gets whatever player two loses. So you model the outcome of a game as some kind of payoff. Somebody gets money, somebody loses money. And zero sum means that the sum of the two payoffs is zero. So if one player is getting money, the other player is losing the same amount. The simplest version of this is where you just have a notion of win or lose. And then this just says that one player wins and the other player loses. Or there's a draw. Draws can fit in here as well. Okay. And what does equilibrium mean? It means that these are strategies for the two players such that knowing the other strategy doesn't change yours. In other words, even knowing the other player's strategy, you already have the best possible strategy. Okay, so what is that strategy for rock, paper, scissors? Yes? Yes, 1/3, 1/3, 1/3, right? If you are playing each of, if you're playing 1/3, 1/3, 1/3, and your opponent announces that they are playing 1/3, 1/3, 1/3, neither of you has any incentive to switch to a different strategy because you will be no better off. Your two strategies are already best responses to each other. Yes?
So when you say like zero strategies, I guess it says it on the board, but I guess just to clarify, is it like specifying a strategy for both players at the same time, or is it like specify like?
Yes, equilibrium is referring to a state of each player having a strategy chosen. Okay, you can't be in equilibrium if you just have I mean, you can have a strategy that leads the other player to choose a strategy that puts you in equilibrium, but equilibrium is about the relationship between the pair of the two strategies. Okay. All right, now we can actually formalize this a little bit. Okay. If we have a pair of players, I will call them Roberta and Colin. I can just write down all of their strategies. Roberta's will be in the rows. Colin's strategies will be in the columns. And at each point in the matrix, I can put the payoff that results if Roberta plays that row and Colin plays that column. Yes? Okay. So we'll call this the payoff matrix. M. Now, for pure strategies, we just read out of the payoff matrix. But what do we do about mixed strategies? So if Roberta has a probability distribution P over her rows, and Colin has a probability distribution Q over his columns, what can we say about the expected payoff of the game? Yes?
Kind of calculate it.
Yes. How would we calculate it?
Expectation of the utility function over their joint distribution.
Yes, but what's the formula for it? I've got all the letters on the board. How should I put them together? Yes? Exactly, right? It's the sum of over I and j of pi qj mij. But we can write that more simply as just pmq, right? Now, I should have said this earlier, but if Roberta is trying to minimize the payoff, remember the payoff is a number that moves from one player to the other. So one player is going to think of trying to move it in their direction and think of it as a negative quantity. So one of these players wants to minimize the payoff, and one of them wants to maximize the payoff, right? Roberta's goal, if we think about it, is that Roberta wants to pick a row strategy, right, that minimizes what the payoff is going to be. But she needs to be worried about what Colin is going to do, right? And Colin is trying to maximize the payoff. So if we're thinking about pure strategies, this is Roberta's sort of pessimistic belief about the outcome of the game, and she's going to want to sort of take the argument here. Yes? On the other hand, Colin is trying to maximize, but is worried about Roberta trying to minimize. That's for pure strategies, but when we move to mixed strategies, now Roberta and Colin are not picking indices, they're picking probability distributions. A mixed strategy is a probability distribution. So Roberta is going to want to pick the probability distribution that minimizes the worst case outcome for the game, no matter what Colin does. And Colin is going to want to do the opposite. Yes? And what von Neumann proved is that these are equal. And that's why we call it an equilibrium. Yes?
So I guess, why don't we stop at just like saying like x of min? So I guess like wouldn't it kind of like keep...
well, so that's exactly the point. There might not be an equilibrium here, right? In other words, Roberta may be thinking, okay, what's the worst thing that Colin can do, and pick a strategy for that. But if Colin now knows that that is Roberta's strategy, then the worst thing Colin can do might change, right? Because now Colin's just thinking about that particular strategy. And so you get this run around that we saw with rock, paper, scissors, okay? However, once you introduce mixed strategies and have probability distributions, there's this very powerful result of von Neumann, which I think I made you prove in advanced algorithms last semester, although I sometimes leave it out and sometimes put it in, that basically you can use linear programming duality to show that these two quantities are actually equal, okay? So that's actually the only thing that I needed to tell you more about randomized algorithm is the fact that these two things are equal. But the story of it is so interesting that I sort of wanted to put that in for your edification. And you should all go off and look at game theory. It's really beautiful. Okay? But now that we have this, okay, what is the relationship of this to randomized algorithms? Well, we can think of designing a randomized algorithm as playing a game against nature. So we already talked about randomized algorithms as deterministic algorithms that run with an advice string. Yes? You give it a random advice string, and let's think about ZPP here. You can tell a similar story about RP, but it's easier to talk about ZPP, which means Las Vegas algorithms, expected runtime, always correct. Okay? So what does a randomized algorithm do? It gets this random advice string. It runs using this random advice string, and that determines how long it's going to run. Okay? Let's think of the runtime. It's a quantity we want to minimize. Let's think of it as a payoff. Okay? However long the algorithm runs, that's how much I have to pay my advisor. Okay? Out of my very large stipend. My advisor wants to make money. So my advisor is going to try to select an input that makes the algorithm run for a really long time. Right? So now we have a game. Right? I have to sort of make choices in the execution of my algorithm. Right? My advisor has to pick an input. Right? What determines my choices? Well, it's this advice string, right? So essentially, the advice string means that you can think of a randomized algorithm as, once you fix the advice string, you have a deterministic algorithm because it just follows the fixed advice string, which means that a randomized algorithm is just a probability distribution over deterministic algorithms, right? So each advice string gives a deterministic algorithm with a deterministic runtime. Okay. The way that I use the advice string determines a probability distribution over those runtimes, or a probability distribution over those deterministic algorithms. Algorithms, right? In other words, a randomized algorithm is just a mixed strategy in the game that I am playing against my advisor. Yes? Advisor chooses an input. Advisor choosing an input sounds a bit like a pure strategy. But now let me go back to the randomized algorithm, back to the game theory for a minute, because there's another really interesting thing that von Neumann proved. Okay? We asserted that these two things are equal. Okay? That if both players are playing mixed strategies, there's this equilibrium. Okay? Now, suppose that Roberta knows Colin's mixed strategy. I claim that Roberta no longer needs a mixed strategy. Roberta actually has a pure best response. Does anybody see why that is? Yes? Exactly, right? So Roberta is thinking about minimizing over her distributions. But if we know Q, right, then we know Colin's strategy, mixed strategy. Roberta is trying to minimize this quantity PMQ for a proper choice of P, right? But MQ is now a constant. It's a vector, right? So what probability distribution will minimize the dot product with that vector? Yes? Yeah, it'll just put a 1 in the smallest term, and that's a pure strategy, right? It's putting all of its weight on a single strategy, right? So at this point, I can choose a pure P, right? And conversely, right, if Colin knows Roberta's mixed strategy, Colin has a pure best response, right? So the point is that to get an equilibrium, you need to introduce mixed strategies. However, only one player has to have one. The other player can be playing a pure strategy. Again, if you start letting the other player make changes based on the pure strategy, your equilibrium goes away. But the point is that the equilibrium is achieved by having one player with a mixed strategy, either one, and the other player with a pure strategy. Yes? So what does this mean for our randomized algorithm story? Yes, it's related to linear programming. Okay, I mean, because of the special properties of these zero-sum two-player games, you can actually home in on an optimal solution if you have the extensive form. Unfortunately, the extensive form tends to be exponential in the size of the game, so it's not a great technique for like solving chess, which doesn't need mixed strategies anyway because it's a deterministic game. All right, so what I said up there about needing only one mixed strategy, how can we translate that to this language of randomized algorithms and inputs? Well, the normal way of thinking about things is that the randomized algorithm is a mixed strategy over my deterministic algorithms. And the best response is some specific bad input for my randomized algorithm, right? There's some input that causes the worst case runtime for my randomized algorithm. But what happens if we flip it the other way? What is another equilibrium situation? Yes. Exactly. So an equivalent situation, but remember, advice string means deterministic algorithm, right? So what is the equivalent outcome can be achieved here if your advisor picks a probability distribution over inputs, and there is a single best deterministic algorithm response with the matching runtime. Okay, so this is the way we usually think about randomized algorithms, right? There's an input, and we're asking about the expected runtime, and we want the worst case expected runtime over all possible deterministic inputs. What von Neumann's game theory equilibrium result says is that you will get exactly the same result if you ask for the worst possible distribution over inputs. What is the best achievable running time for a deterministic algorithm? Sorry, it's an expected running time, right? But now the expectation is over the input distribution. So I said that we will almost never talk about input distributions, right? But here is a case where we are because it's actually equivalent. Okay. Yes?
I can definitely see why this is helpful for analysis. But I guess I'm just wondering, I guess, how can we say like if they both have like a mixed strategy in this equilibrium, how can we like say like that fixing either P or fixing Q as random, like how can we say that this can give the same result?
That's exactly what we showed on the top board, right? That once you fix Q, there's a P with the 1 in a single coordinate.
Well, yeah, but I'm saying like if you go the other way and fix like Q or whatever, and then fix P or fix.
Yeah, but that, I mean, it's symmetric, right? If you fix one, you can set a single one in the other one and get the same result. Okay. So I can now summarize this as Yau's minimax principle. So let me put it on a different board. When I was looking for a job, I visited Andy Yau at Princeton, and he had a beautiful office with literally nothing in it. He was sitting at his desk, which had nothing on it, and his bookshelves were completely empty. It was a pretty creepy visit, actually, like to Princeton in general. They're like, because you meet all the faculty, but like the faculty that I was meeting was in the building, but as far as I could tell, nobody else was. So it was just like me and one other person in the building all day long. Just the people kept changing. So Yau's minimax principle says that the, whoops, am I on the wrong page? Says that the worst case expected runtime of a ZPP algorithm is equal to the best achievable expected runtime of a deterministic algorithm on the worst possible distribution over inputs. Okay. Sorry, I left out a best here. Right, so we are looking for the best possible ZPP algorithm. So the best worst case expected runtime that we can achieve, okay, where we're designing an algorithm and trying to work on the best, as best possible on the worst possible input, is equivalent to the best input that we can achieve by being given a probability distribution over inputs and designing the best possible deterministic algorithm for that particular probability distribution over inputs. Okay. Now, it's often difficult to design the best possible algorithm, but we can use this as a lower bounding technique. How do I use this as a lower bounding method? I pick a distribution over inputs, and I show that no deterministic algorithm does well. Right? If I give a lower bound on the behavior of any deterministic algorithm on a particular input, that provides a lower bound on the best possible behavior of a randomized algorithm. Yes?
So in this score, we said that there's as your best response.
Yes.
We're also claiming that that is the same expected value as the equilibrium.
Yes. And that's what's going on here, right? In equilibrium, in the normal notion of equilibrium, I would have a randomized algorithm and my advisor would have a probability distribution over inputs, but that's not necessary, right? if my randomized algorithm is known, my advisor can pick a particular bad input. If my advisor specifies a probability distribution, I can settle for a deterministic algorithm and get the same expected runtime. Okay? So now we're finally at the conclusion that we have a way to lower bound the expected runtime of randomized algorithms just by analyzing a deterministic algorithm. We still have to think about the probability distribution over the inputs, but at least the algorithm is deterministic. Any questions? Yes? No, so when I say a pure worst case input, I'm talking about our standard, the way we usually think about algorithms, which is I have a randomized algorithm. How do I define its runtime? I talk about its expected runtime on the worst possible input. In other words, each input is going to give it a certain expected runtime, and I want to talk about the input which gives the worst expected runtime. And that is my definition of the expected runtime of that algorithm. Okay, or the worst case expected runtime. And that is what we can equivalently find by, so, the expected runtime of that best possible algorithm is equal to the expected runtime of the best deterministic algorithm on the worst possible distribution. There was another question? No? Okay, so let's think about how to use this. Right? How do we use this? Well, let's go back to our game tree example. Okay. We want to show that no randomized algorithm does well, that there's some input that causes every randomized algorithm to take a long time to evaluate that input. Right? According to Yao's minimax principle, one way to do that is to give a distribution over inputs. In other words, a distribution over game trees, and then argue that no deterministic algorithm can quickly evaluate one of those randomly generated game trees. Okay? And here I mean quickly in expectation because it is a random game tree, so the time that it takes to figure it out may be random. Okay? So the work now goes to thinking of a clever distribution. And I'm going to suggest one to start with. I can choose a distribution where each leaf is a loss with probability p, which I'm going to set to be 1/2 of 3 minus root 5. And a win with probability 1 minus p, which is equal to 1/2 of root 5 minus 1. Now, why did I pull these weird numbers out of my hat? Well, the reason is, if we have a parent node, right, and each of the two children is a loss with probability p, okay, you can do the math, I won't do it for you, and conclude that the parent also has a loss probability of p. It's a fixed point. Okay? So if I set every leaf independently to be a loss with probability p, then in fact every node of the tree is a loss with probability p. Okay. Actually, sorry, I will fill in the math, right? So the probability of a loss is equal to the probability that both children are a win, which is equal to 1 minus p squared. And if you sort of plug in the value of p that we have, this turns out to be p. Okay. Now, you may remember from last time, and I'm going to finish up the argument here, that any deterministic algorithm, or at least the best deterministic algorithm for any tree, should fully evaluate one child before starting to evaluate the other. I used this argument last time when I sort of said that what the best deterministic algorithm should do, right? So I'm resurfacing this argument and saying, you know, the deterministic algorithm can choose whether to do the left or the right first, but that's really the only choice for the deterministic algorithm to do, is which tree to evaluate first. But as you can see, right, this whole tree is sort of symmetric and random, and so it doesn't really matter which child the deterministic algorithm chooses to evaluate first, right? And if the first child is a win, then you have to evaluate the other child, right? Because if the first child is a win, it's the outcome of the second child that tells you whether your node is a win or a loss, right? I'm going fast through this because it's the same arguments as we made last time. Stop me if anything is not clear. Okay. So we can now analyze the runtime of our deterministic algorithm, right? It's going to evaluate one subtree, one child, and then if it has to, it's going to evaluate the other child. And so what that means is that T of H is equal to, well, with probability P, you're just going to evaluate the first child, but it's going to be a loss, which means you can stop, because that's the move you should make, right? On the other hand, with probability 1 minus P, you're going to have to evaluate both children, because the first one was a win, right? So we've got P plus 2 times 1 minus P times T of H minus 1, so this is just 2 minus P to the H, which turns out to be n to the power of 0.694 if you plug in all of the numbers. Okay. So we have a lower bound on the running time of this deterministic, or we have a bound on the time for this deterministic algorithm, which is the best possible deterministic algorithm because there aren't really any choices for the deterministic algorithm to make. And so this lower bounds the expected running time for any randomized algorithm on any input using Yau's minimax principle. Now, this is not quite satisfactory because the upper bound that we had was n to the 0.75 or so, right? So what that tells us is that we didn't really pick the best possible distribution. Can anybody see why this distribution is kind of giving too much away to the algorithm, making things too easy? Yes? Exactly. If I am constructing a bad tree to evaluate, right, then if I make both of the children lose, right, that makes the, sorry, if I want to make a node win, it has to have a losing child. But if I make both of its children losing, then it becomes easier for the algorithm to evaluate. So the fact that I am making these independent choices of leaves and therefore making siblings independent of each other creates a certain probability that both children are losses, which makes it easy on the deterministic algorithm. Okay? So you need to come up with a better distribution which has a sort of win-win situation with some probability P that will make your node a loss, and a win-loss with probability 1 minus P, and never or a loss win, right? One child wins and one child loses, and you never have both children lose. Okay, and so you don't do this with independent choices at the leaves. Instead, you figure out what P you need, and you sort of work down from the root to make this distribution happen. And in that situation, you get an exact match to the upper bound. So Yau's minimax theorem gives you a tight result and proves that the algorithm that we talked about before was optimal. And that's not very surprising because there isn't actually a lot, but there's not a lot clever that you can do in this very restricted game tree evaluation story, but this gives us a way to prove it. Okay. Any questions? No? All right. Yes, go ahead.
Yeah, I was kind of going back to the equilibrium. I'm like, I guess I understand what you're saying about like if you know Q and P shadows. But if like something like that small, Q now is P is one change.
Right, well, so again, the notion of equilibrium comes from the idea of each player having a mixed strategy, right? And so this is just an observation about how you can simplify that. You can get that result of the mixed strategy with a simpler description. Okay, yes? Exactly. 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 That's right. And that's what we used in Yau's minimax principle, is that you can make one of them deterministic without changing the value. Okay. Other questions? Okay. Let's take a break, and then I will show you some more interesting tricks for analyzing randomized algorithms. All right, I see basically everybody's sitting, so clearly you can't wait to get back to learning more about really exciting algorithms. So let me resume. We are currently in the sort of the stage of introducing tools. So I am very soon going to show you some very interesting algorithms, but right now I'm showing you sort of toy or simple algorithmic problems because they let me show you the techniques that we're going to be using. I want to talk a little bit about an interesting topic. Actually, just before I get started on, so the topic I'm going to be talking about is stable matching, which I will introduce in a minute. But first, let me do a little review of the coupon collector problem, which hopefully all of you have seen. But I want to make sure that everybody's caught up, and it lets me talk about linearity of expectation again, which is the most common hammer we'll be using in this class, right? So the idea here is that there is a set of n different cards or coupon. This is, collecting baseball cards was a typical example used, but I don't think anybody does that anymore. You get a sequence of coupons, each of which we can think of as a number from 1 to n, and each member of the sequence is uniformly and randomly chosen from that set. And the question that you want to ask is, how long until you see all of the coupons? So who's seen this problem before? All right, not everybody. Let's do a quick analysis. How do you solve this problem? Yes?
So we count the number of turns to like coupons we need to see until we get like the first coupon.
Exactly. So we can write this as a sum, right? How long does it take until we get the first coupon, and the second, and the third, up till the nth coupon, right? Now, how long does it take us to get the first coupon? One time, right? It's right away, right? Now, how do we figure out how long it takes us to get the second coupon? Yes? Exactly. That's right. So the point is that each time we get a random coupon, there's a chance it's the one we've seen before, the one we've got. But n minus 1 out of n of them are going to be new. So there's an n minus 1 out of n chance that we get a new coupon on each try here, right? Which means that the expected time to get that second coupon, this is another fact that you should lock into your brains because we'll use it all the time, is if you have a certain probability of something that you're waiting for, the expected time until it happens is just 1 over that probability. Okay? So this is the expected value of T2. By the same argument, the expected value of T3 is n over n minus 2, right? And so on down the line, okay? And these are random variables, and but because of linearity of expectation, we can just add up these different expectations. We get 1, which is just n over n, plus n over n minus 1, and so on, all the way down to n over 1, right? Which is n times the nth harmonic number, which is approximately n times the natural log of n. But I'm not worrying about constants, so I'll just call it n log n. Okay, so that's the coupon collector problem, which I will not dwell on because most of you have seen it before, but make sure you're familiar with it and with the techniques used to derive that result. So now let me talk about stable matching. So this is a problem which actually, the stable matching algorithm is run for very important reasons every year. So the problem is that you have a bipartite graph. Okay. You have n entities on the left, which I will call students. And you have n entities on the right, which I will call schools. And the idea is that each student has a preference list of all the schools, just a ranking. Okay. And similarly, each school has a ranking of all students. And our job is to match up the students in the schools. One student to one school to one student. We want to find a perfect matching. That is stable. What does it mean for the perfect matching to be stable? It means that when we announce the perfect matching, there is no situation where a student and a school will collude to do something different than what we've announced. What could cause the matching to be unstable? So that one student and one school could say, no, 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 we're going to make a different choice. Yes? But this is, the way you're talking about it, you've got multiple students talking to multiple schools. So I'm asking for a stability where no one student and no one school are going to by themselves mess up the plan. What would cause one student and one school to mess up the plan? Yes? Exactly. So we define stable in contrast to unstable, where some student and school prefer each other to the current match. Right? The school likes that student better than their current student, and the student likes that school better than their current school, and so that student and that school will run off together and leave their matched student and school without a partner. Yes? Okay. Why is this important? Well, what is this used for? Does anybody know? This will matter to some of you, I'm guessing. This is how they match medical students to residencies. Okay? There's a link in the notes. You can read about it. Okay, so you don't want a medical student deciding that they would rather go to a different school and that school wants them over the medical student that they got. Okay? So is the problem formulation clear? All right, so the first and most obvious question is there a stable matching? Could we get into a situation where no matter what we do, the different students and schools just keep on negotiating behind our backs and it never actually settles down? Well, the answer is yes, always. And the way we're going to prove it is by giving an algorithm that always yields a stable matching. I should also say, historically, when this problem was introduced, it was called the stable marriage problem. I think that, and it was talked about in terms of men and women, I think this is a better story because we actually use this to match students to schools, but this is not how you match men and women, right? So we'll focus on this scenario. And let me describe the algorithm to you. This is another case where I'm giving you a very long lead up to just show you one simple thing about randomized algorithms, but it's fun culture. So hopefully you enjoy it. So the algorithm is known as the proposal algorithm. And it's not fully specified, actually. There's a little bit of arbitrary choice in it. Or sorry, I didn't say that properly. Yes, I did say it properly. You rank the students, or just order the students. Arbitrarily. And now you repeatedly apply this rule, which says that the earliest in the order, currently unmatched, student proposes to schools in preference order. Right? This student has a particular ranking, starts at the top of the ranking, says, will you take me? Right? And if they get a no, then they go on to the next one in the ranking, and they just keep working down the ranking until somebody says yes. Okay, now, why might they get a no? Why would a school refuse a student? Yes?
They've already admitted someone who, like, the school ranks higher than.
Exactly. So they keep going until they get a yes, because they propose to a school with either no match, which is great, or a match the school likes less. In which case, that old match is, well, kicked out. Right? Well, so they're back in the pool, right? And then you go back and find another student who may be that one, and they start proposing again. Yes?
Does it matter if you like put that person that just got, like, does it matter where you put the unmatched person?
It doesn't actually matter. Okay. Yeah, because this order can be arbitrary, and I think it can even change. But I might be wrong. We'll see if as I continue the presentation. Okay. So this is the algorithm, and it continues until every student is matched. Which, on the surface of it, might be forever, right? It looks like, we might keep kicking out students who go off and propose and kick out other students and so on and so forth. But the termination condition is when every student is matched, okay? However, it turns out that this terminates in finite time, okay? And the proof is pretty straightforward, which is that the situation of any school only improves over time, right? From the perspective of the school, it's initially unmatched, gets a proposal, it accepts the first one, and then it only takes better and better students from its own perspective, right? So there are only n rejections per school, right? Notice also that matched schools stay matched. So basically, you can have n events where a school accepts because it's empty, one per student, or sorry, one per school. And then for each school, you can have n rejection events where they kick out somebody, okay? But that only totals to about n plus 1 events per school. And each proposal results in one of those events, right? So after n squared steps, all these events are used up. Okay? So only n squared proposals are required in order to in order for this algorithm to necessarily terminate. Yes? And since the algorithm terminates, and it only terminates when you have a matching, this tells us a matching exists. But now the question is it stable? Okay. Let me prove that. Let me prove to you that it is. So suppose it's not. Okay. What does that mean? That means that you have an XY pair that are unsatisfied with the current arrangement. Which means, sorry, they're not a pair with each other. They want to be a pair. In other words, you have an XX and a YY, two pairs, but X prefers Y, little y to little x, and little y prefers big X to big Y. Okay, that would be an instability. Okay. My claim is that this can't happen, and I'm racing through this because this is all deterministic stuff, and this is a randomized algorithms class. The point is that if X prefers little y, it means that X proposed to little y before proposing to little x. Yes? Because students propose in preference order. So if X proposed to Y first, why is X currently matched to little x? Yes? Exactly, right? X was rejected by little y. But y keeps improving its choice over the course of the algorithm. So little y prefers big Y. So that proves that at the end, that when this algorithm is always sort of locally stable, and when it terminates and is a perfect matching, it is in fact a stable matching. Okay. All right. So this is not a great place to stop because I ran out of time before the sort of main point of this, but I don't want to keep you past the end of class. So I will finish off this argument on Friday, and then we will start talking about tail bounds, right? So far we've only been doing expected analysis, but as was brought up a couple of lectures ago, sometimes you care not about the expectation, but about the likelihood that the algorithm will run for a long time, and I'll show you some methods for analyzing that on Friday. Any final questions? No? All right, I'll see you Friday.